Hello everyone, and thanks to the organizers, Dan, Amit, and all the organizers for the great workshop. And I don't know if it's a good thing to finish the workshop with some kind of negative result. I certainly don't mind, but I don't know what the effect on the community is. So I'm going to talk about some impossibility results, in particular some lower bounds on the assumptions that we can use to build I/O. And it's going to be about all-or-nothing encryption primitives. It's a joint work with Sanjam and my student Amir. Okay, so the talk is about I/O. I'm not going to define it, so you have it on the picture. What is interesting about I/O is that, well, it is basically giving us a lot of things that we were looking for. Almost anything you can ask, and you would have it next week or next month or so. So it is important to understand whether the assumptions that we build I/O upon are something that we have good trust on or not. Like, we certainly prefer something that is well, more understood, more believed to be secure, and we want to understand which ones we can use. So this picture, we borrowed it from a paper by two authors very recently put on ePrint. It shows you different paths that go eventually from getting an input circuit and getting an obfuscated version of that circuit, and the paths go through a lot of different nodes, but they all essentially go through one or other form of multilinear maps at the end of the day, or graded encoding scheme, as you wish to call it. So if I want to simplify the picture, we have I/O, but basically we have to start from multilinear maps, which are a little bit under scrutiny, at least recently, and we get attacks every now and then. And there is another path to get there, which goes through compact functional encryption, but that path also kind of starts from multilinear maps. So again, the question is, can we use quote-unquote the standard assumptions, things that, it's not a formal statement, but things that when we see, we know it. For example, LWE might be a very good assumption to use to build I/O if we can eventually. So what is known about this question? Well, the positive side is basically this, but there is a negative side that tries to kind of sandwich where we can eventually go, starting by being very, very ambitious, trying to say whether we can get obfuscation from one-way function. We didn't know that even last year, but there was some technical reasons that we didn't know it. But eventually things started to get better, so we understood, well, you cannot get it from one-way function, you cannot get it from hash functions, and so on. So this is not a possibility, this is impossibility. I should have pressed it faster. But what is this impossibility? What is the model in which this impossibility is proved? Well, the model is basically the only model that we had so far. So we had this line of work from starting from Impagliozzo-Rudich's very influential work, that they said, look, a lot of constructions are black box in a strong sense, and sometimes you cannot do things in a black box way. What they meant by black box, I'm oversimplifying, but what they meant was that suppose you want to do I/O using some primitive P, you basically shouldn't look inside the P. You have to use only the input-output functionality of that primitive. For example, whether it's one-way function or something else, you shouldn't look inside. This model and the impossibility results that are proved against this model, they actually make a lot of sense when this primitive is something like one-way function or hash function, because when we use one-way function alone, when we use hash functions alone, we basically use them in a black box way, almost always. However, things quickly change when you have other players that come into game, and you have things other than one-way function or chapter permutation as one of the primitives that you use. How about some primitive P that I would call it self-feeding, something that is a little bit more complicated and at the same time more powerful? And what would mean to use P to get something like I/O? And let me clarify what setting we are talking about now. So this primitive P might have two subroutines. For example, think about something like functional encryption or attributed encryption. I will go over them, but it has a bunch of subroutines: key generation, encryption, decryption. One of these subroutines, for example, P2, is a special one that you can feed this a circuit or a general algorithm. It takes as input some piece of code. So this is not the case necessarily for one-way function. The semantics of the input doesn't say it's a circuit. But here, P2 anticipates you to give it an algorithm as a circuit. So when we are constructing I/O, we might use this fact. So we might actually give as input some circuit C to this primitive, to this subroutine P2. And if you look at this circuit that we are giving this, we are giving to this subroutine P2, it might actually use the primitive itself, potentially. So I might have the code of the primitive P that I'm using somehow planted in a non-black box way inside a circuit that I feed to P itself. So this is something that makes the construction eventually non-black box, because in order to really implement this at the end of the day, I really need the code of P1 to really plant it to feed it to P2, because P2 anticipates a circuit as input. So this kind of doing something like this makes your construction non-black box. This is not anymore in the framework of Impossible-Rudish. Nevertheless, we do it all the time. So this is a very popular technique. This is basically the source of most of the non-black box phenomenon that we have. Let me give you a couple of examples. So examples where this trick is used, this is a list of 3 items. You can probably add 20 more to it. So for example, when we are bootstrapping the construction of homomorphic encryption, as Gentry did, if you look at what we are basically doing, we are giving a circuit to the evaluation algorithm where this circuit has the decryption gates, the decryption algorithm in it somehow. Or if you want to bootstrap I/O, we are doing kind of similar things. We are obfuscating a circuit that this circuit has some FHE algorithms planted in it. Or kind of more relevant to this talk, if you look at the construction of obfuscate I/O from functional encryption, which was proposed last year by Anand Jain and Bitansky Venkutanathan, they are going to use a functional encryption scheme basically with this trick where you would generate keys for a piece of circuit, for a function, where that function uses the encryption algorithm itself in it. So these are examples where we are using this trick. Therefore, all of these results basically fall out of the Impossible-Rudish or RTV's framework. So because of this, if we want to prove an impossibility result that deals with these kind of primitives, we have to actually, if we want to prove something meaningful that tells us what is the limitations of our techniques or what you should anticipate to be published in near future, we have to really work with a model that this is built into the model. And when we say something is impossible, we cover all these tricks, this trick in all various forms that it could be applied. For example, what this slide is going to tell you is that informally speaking, we can have something that we call it an extended black box model. It's not black box in the traditional sense. If you have a good name for it, please tell us. We're looking for it because we think this is a very natural notion. We tried 10 different names, and then we just said, let's call it extended for now. So it's called extended black box model, where if you use a primitive P, which is a special, we can formalize what it is, but think about something like functional encryption or some primitive that takes a circuit as input. If you're dealing with such a primitive P which has a bunch of subroutines, your construction of I/O or anything else is allowed to use circuits and feed them to the subroutine P2, which is a special subroutine that anticipates something like that, where you can arbitrarily plant gates of the primitive P itself there.
I have a question.
Sure.
What if you wanted to take a primitive from P2, but then you first want to do a randomized encoding of it, and then give the result of that? Would that be in your framework, or is that outside?
As long as you do not, as long as all you do is to
because now it's no longer a P2 gate. Right?
so if you define the randomized encoding as a primitive itself, then eventually you're feeding a circuit to it. And if you are working in this model, you're allowed to put any gate there. So eventually your primitive, you have to first say what my input-output behavior for the primitive is. Formalize your subroutines. Some of these subroutines as input, they take circuit. And in that particular circuit, I can call my own primitive arbitrarily. So that's the model.
A primitive usually has some cryptographic security guarantee, whereas like a randomizing encoding is it's not really a cryptographic object, it's like a technique, right? It produces.
Well,
I'm not sure if it would.
if you can formalize random encoding as a primitive, you would be allowed to do so in this model. So let me.
Maybe this is asking these questions. Can you give an example of something that's not in the model?
Yeah.
Which is not in model. So for example, when we go from, so you mean something that we could use it and we didn't use it?
No, something that's outside of the extended black box model.
Oh, do we have anything out? So we have techniques that are not necessarily like this. When you open up a circuit and you go gate by gate over it and to do something like a garbling, you might not be able to put it in this framework.
But a garbling is the same thing as randomized encoding, so that is outside.
So if you go over something gate by gate,
The primitive itself, right, that where it takes a circuit as input, output something, then it would need the model. If you take it, open it separately, then it would.
to tell you honestly, I don't know anything out of this model. Everything, my guess is that if I can formalize that technique as a primitive, most likely this would fall into this framework. But the examples that I had, I see them in their model, and the primitives that we eventually deal with, for those primitives that we kind of prove theorems in this work, for them it's clear what it means to work in the extended black box model. But your question is basically general about this model. It's better to first know, so as soon as you know your primitive clearly, it's more clear what is allowed, what is not allowed. But this picture is better to be imagined with your favorite example, other than random. So this is basically a model that was partially studied before in some impossibility results. So this is kind of inspired by the works of Bitansky, Katz, Segev, and Yerikumovich, and Asharov Segev. What they did, they proved some impossibilities that in those theorems, they allowed certain gates to be in the circuits that you use, but not all possible gates. So none of those results were proved in the full extended setting. And in fact, the controversy around some of these separations that were proved a few years ago, and now we know how to detour them, how kind of prove a non-black box result of, say, going from private key functional encryption to public encryption, is basically for the exact reason that impossibility result excluded some of those gates. The possibility results are taking advantage of it. They're planting something there that the impossibility result kind of prevented you from doing in the definition of the model. Okay, so at a high level, I hope the model is clear. If it's not, let me know, because I want to now work with this model. So as I said, the key point here is that every gate is allowed. You should, if you claim that I cannot use P to get I/O in an extended black box way, you should be able to argue that no matter how you plan those gates, it's still not possible. So what is the main theorem that we prove? Well, pick your favorite all-or-nothing encryption primitive. What do I mean by that? Some encryption primitive, one of those that I mentioned, where either you have a key and you can decrypt your message completely, or you don't have the right key and you are not supposed to learn anything. Let me give you the concrete list. So the list includes things like attribute-based encryption, predicate encryption, witness encryption, fully homomorphic encryption. There are more things that I didn't list it here because if you pick something given out of here, I might be able to tell you that actually I can fit it there. So the list is long, and these are, with the exception of witness encryption, actually the rest of them we have by now pretty good understanding of how to do construct them based on good assumptions like LWE. What we prove is that if you pick anything from this list, you are not going to be able to get I/O from it in the right model that you should prove the impossibility, basically in the extended black box model. So for example, predicate encryption is not going to be useful to get I/O if your construction falls into the picture that I had in the previous slide. As long as it is like it, and let me emphasize that this picture, this innocent looking picture, you might end up with a completely nested circuit there. Like P2 itself might be fed something that has another gate in it. So there is no limitation on the depth here other than just being polynomial. You can arbitrarily, as long as it's polynomial size, when you open it up, it is allowed here. Okay. So this is the main impossibility theorem. And in the rest of the talk, I want to tell you some ideas about it, how to prove it. But before doing that, one more theorem that we prove, which is actually not proved in the extended black box model. It's proved in the traditional model. Let me tell you and why we cared about it. So the construction of functional encryption to I/O, by the last year construction by these two papers, they are, as I told you, they're non-black box. They are in the extended black box model. Another work, Rachel Lynn, she said if you could make this actually fully black box, and if you avoid planting gates, if you can make it fully black box, she could give you something amazing from it. She could then eventually base I/O on LW plus some PRG. So this was used as a kind of, I wouldn't call it a conjecture, but as like something that at least if true, I could get something interesting. So what we show is that, well, at least this is not going to work. So using the techniques that we use to prove our impossibility results, we can rule out the fully black box construction of I/O from FE as well. So it's a different flavor. Qualitatively, it's a different result. We wouldn't call it an impossibility result in the first place because there is a way to get away around it, but it would have had applications if it was true. Unfortunately, it's not. So now I'm going to tell you a little bit of high level of what's going on in the proof, and then getting a little bit into the details. So at the very high level, the way we prove our impossibility results is to prove certain impossibility results for variations of witness encryption. So in particular, we show that witness encryption is not going to give you I/O in an extended black box way. Moreover, some stronger forms of witness encryption are still not going to give you I/O. And the way that we get all those theorems is that we show that all these variations of witness encryption are basically sufficient in an extended black box way to obtain attribute-based encryption, predicate encryption, fully homomorphic encryption, and so on and so forth. And because we studied this model in a kind of abstract way, we prove that extended black box constructions are, roughly speaking, transitive similarly to fully black box constructions. Therefore, if you have, similarly to previous result, if you have an impossibility result, and if you prove some possibility result from them, you can actually also conclude that these primitives are not going to give you I/O, because if they could, you would have a way to go from witness encryption to I/O, which is ruled out by the first theorem. So the heart of the matter is to prove those impossibilities for witness encryption and the variations of it. The rest of it would follow by proving kind of easier positive results. Any question about the high level? Okay. Now I'm going to focus on ideas behind how we actually prove the main separation about witness encryption and some variations about it. So now we just focus on this impossibility result. But because we want to actually say the proof, let me be a little more specific and give you a more concrete picture of what it means to use witness encryption in an extended black box way. So suppose your primitive is witness encryption. What is it? You are able to encrypt a message M under some function F, circuit F. Later on, if you are using some quote-unquote witness W, if that witness can satisfy your circuit, you would be able to decrypt M. And if F is not satisfiable, basically it's an indistinguishability security provided. So what is an extended black box use or extended black box construction from witness encryption? Well, basically what it means that you can use a function F here in your encryption, that your function F could have encryption and decryption gates in it. It could call those primitives as a black box themselves. But eventually, if you have such a construction, if you want to realize it at the end of the day, it would become non-black box. In our model, we just call it black box because that's allowed in the model. So one simple observation is that we can, instead of saying the construction is kind of non-black box and is planting these gates, we can make a trick saying that it's equivalent to say that we are still using a primitive in a black box way, but the primitive itself is extended. So the primitive itself is a form of witness encryption that it allows you to have oracle circuits as input instead of just circuits. So we push the kind of non-black box part to the primitive and say the primitive is more powerful. These two are actually equivalent. So basically, we are going to work with the second form of the interpretation, where we are back to fully black box constructions, but your primitive itself has become much more powerful. It can have kind of nested calls to itself through this framework. So what it means that now, if you want to prove an impossibility, we want to say that extended witness encryption cannot give you I/O, for example, in a fully black box way. But we are not going to get free lunch. Still, the primitive itself is so much more powerful now, so we should be careful. So I want to quickly say something and go over it. I want to say that by now we have a good understanding, at least one technique of how we can prove impossibility results for I/O, which is the way that the results that I mentioned at the beginning of the talk, they follow this recipe. Because we are now back to proving impossibility results in the fully black box setting. The point is that our primitive is much more powerful. Nevertheless, we are going to use the same kind of general high-level technique of proving impossibilities for I/O. I would need new ideas for handling the witness encryption itself. But the general framework says the following. If you want to say that some primitive P doesn't give you I/O, it is sufficient to do the following. You first have to define some idealized oracle that gives you that primitive P. In this case, the primitive would be actually extended witness encryption. And this is usually easy. You just define an oracle that basically takes things and gives you random labels and does everything correctly. But the challenge is to show that you can compile out this oracle from any I/O construction that tries to use this idealized oracle. So this idealized oracle is like a very strong form of P. Suppose you could construct I/O from it. If you can actually compile out this oracle and get something close to I/O, which is called approximately correct I/O, where you're back to the plain model, but your correctness condition is a little bit hurt, and it's only correctly 99% over the input. If you can only do so, we already know that you can conclude that there is no fully black box construction of I/O from P. And the result basically follows from combination of several arguments. At the heart of those arguments is a recent result that says there is no statistically secure approximately correct I/O, which means that after you compile out your oracle, there is a computationally unbounded attack against that construction. And by going back, you can get a computationally unbounded but polynomial query attack in the idealized model. And that's basically enough for black box separation. But keep in mind, our goal is simple. We want to just compile out P, and we know that's enough, but we have to make sure that the oracle P is actually giving us extended witness encryption. Okay, this is the high-level recipe. Okay, so what we're going to do looks simple. We're going to do this. We have an oracle P that, for example, in this case, is going to implement extended witness encryption for us. We start from an I/O construction that uses that oracle. And hopefully, we will turn it into an I/O construction in the plain model, which doesn't use any P, but is only approximately correct. We have to say how to obfuscate, how to basically design this algorithm, and how to evaluate it. We have to describe both processes. But let me be a little bit more into the process. Let me try something that doesn't quite work, but is very intuitive. So if you want to get rid of your oracle, one thing you can do is you can do lazy evaluation. Because these oracles, usually, if you simulate it from the beginning, you can kind of simulate the next answer. There is no oracle accessible to everyone, but if you're just answering one party, you can keep answering them consistently. For example, we can simulate a random oracle trivially by just having a short table. A random permutation, we need a little bit more care. Trapdoor permutation, a little more, but we can always do lazy evaluation. So suppose you start from your construction of I/O in the idealized model. One trick is to basically say, well, there is no oracle anymore. If you want to ask, if your algorithm, I/O algorithm, wants to ask anything from your oracle P, just simulate the answer. It doesn't make a lot of sense, but it looks like at least we can finish the obfuscation. We obtain some obfuscated code that looks like an obfuscated program. Let's call it B. And the point is that we have to be able to evaluate P later on. Well, one trivial idea is that when you try to evaluate B, B might also try to call the primitive P, keep simulating the answers, from scratch. The problem is that it is a secure thing, so nobody would break it, but it's not going to give you the right answer because the emulation on the left side and the right-hand side are not even consistent. So you answer something in the green form, it has nothing to do with the evaluator's randomized simulation of the Oracle P. On the other hand, if we completely reveal what we did on the left-hand side to the evaluator, now we can guarantee that you get the right answer, but you lose the security because you basically reveal what happened on the obfuscation side. You reveal all the details of how you obfuscated the code. So basically, we have to find some middle ground. We have to say, I'm not going to reveal all of these green things to the obfuscated code, but part of it, so that you can still manage to evaluate the circuit correctly, and it's small enough to guarantee that you didn't learn much. So it's going to be something between these two. So there is a technique invented by Kenneth Paneth. They proposed this general idea of how to do it, and we're going to use the general idea applied to the witness encryption. So the general idea, it can be applied to anything. What they say is that, well, after you simulated your Oracle using lazy evaluation and kind of simulated the green answers for your obfuscation algorithm, you obtain some piece of code B. Instead of immediately outputting B, let's just run B on a bunch of random points and extract some information that could be obtained by anybody who has this B. Because in my original algorithm, B, after I output it, everybody could run it. In particular, everybody could give it a random input. So let's do it a couple of times. Let's run this algorithm B on T random points, and let's see what queries are going to be asked in those T executions. So this is an information that it is safe to pass it along with your obfuscated code as long as you only care about approximate correctness. Because what you have done, basically, you have gathered what is more likely to be asked when you eventually run your algorithm on a random point. And what you reveal is obtained by just running it on a few random points. So that B prime would be your obfuscated code, where B prime is your original simulated obfuscated code together with what you gathered by running B on a bunch of random points. The orange oval says this is the set of queries that you discovered. It is safe to reveal it because technically a simulator could extract that information in the ideal as well. So the proving security, it should be based on some simulator. The point is that the fact that this is secure is easy to prove. I just sketch it for you. The whole challenge for every specific Oracle is to prove that when you have that information, you can actually run that program and get approximate correctness. This is different for every task. So for random Oracle, it's easy. When you move to constant degree graded encoding, you have to do more algebraic arguments there. And every primitive has its own argument there. So what is now the challenge specifically that shows up when we are dealing with an extended primitive, like a witness encryption that we can have nested calls to itself? What is really showing up here as the new challenge? The point is that when you run this algorithm B, the obfuscated code T times, it is not clear what you can now pass along the piece of code to the right-hand side. Why? This is the key point. So your circuit F that you are giving to the encryption algorithm, as we said, the whole point of this model is that that circuit can call its own Oracle queries. When you call when you have an Oracle or some algorithm that you give it and does the job for you, you do not have a control of, eventually when you do the decryption, you do not have a control on which queries are going to be asked in the decryption phase, because you don't see the function F. What it means that every time that you deal with this Oracle, there are two levels of queries. The second level is the queries that are asked by the function F, and you don't necessarily see what those queries are. When you are encrypting something, you choose what the function F is. But if you are doing a decryption, for example, that's where the function is being executed. That depends what witness is used. You don't have any idea necessarily. You might have some idea, but you don't know in general what queries are being asked in the nested layers inside those. So there is something going inside behind the doors. We don't see them. So this is what I show by these black circles. So the Oracle queries themselves have their own kind of second hidden layer. And the point is that we can still simulate them because we are doing everything on the left side. There is no Oracle. We are doing emulation of the oracle ourselves. But those parts are not safe to be passed to the right-hand side because in the ideal world, they're not visible. We don't see them. So we cannot prove security by just planting them on the right-hand side. It's not safe to pass them along, but we need them. So they are not visible. Now there are two ideas that I want to quickly mention without getting into the details. The point is that for some settings, for witness encryption, we can make those hidden queries visible kind of for free. Why? Well, look at witness encryption. This is the definition. We can encrypt, we can decrypt. There is a function f. The function is allowed to have oracle calls. The point is that it is safe to reveal this function f all the time. It doesn't hurt the security of witness encryption. I would call it an instance revealing witness encryption, that whenever you have a ciphertext, there is an efficient procedure to extract what function you have inside that ciphertext. So if I can see what function is there, it means that every time that there is a decryption process being executed, I would be able to efficiently extract everything that is asked inside there. Because first, I can extract the function f from the ciphertext. I have the witness. I can run it myself. In addition to the witness, in addition to the decryption algorithm, whoever has that information, ciphertext witness, they would know whatever happened inside there. Which means that if the primitive was extended witness encryption, this is kind of a simple trick to make sure that all these black circles are not black anymore. They could be, with like a simple modification to the algorithm, everybody who is calling a decryption query, for free, they have access to a list of what is asked inside that. So you have a
I just want to understand by contrast. So
Sure.
Can you go back to the previous slide? Yeah, this here.
Yes.
So this should not work for functional encryption, right?
This doesn't work for functional encryption.
I don't understand why. Because so you're saying that
No, for functional encryption, actually you can still, the trick still works. The rest of the proof doesn't work.
okay.
So you can, for functional encryption, so I'm going, exactly. So the point is that when I make this trick, the witness encryption becomes something like a random oracle. So what is left there? Basically, you have an encryption algorithm that is kind of randomly encrypting, and every now and then you just reveal the whole pre-image. So some points get completely revealed. And the functional encryption huge difference is that the functional encryption is fuzzy, and the fuzzy means that sometimes you just learned a little bit about your input, a little bit more, a little bit more. You still have no idea what the whole input is. You can. This part doesn't care. This part would break down when you go, for example, to predicate encryption, where the function is supposed to remain secret. So this trick doesn't work there, but implicitly, every argument that eventually I would make, and some of them I would go over them, some of them not, they would rely on the 0-1 property of this primitive. So that is already extremely important for the proof, that the primitive itself either reveals the whole plain text for you or none of it. And I'm just focusing, that's kind of implicit somewhere in the proof that breaks down if you use start from function encryption. However, I also told you, we have a separation of fully black box separation of function encryption too. That result uses the same exact trick. So we still use this trick when we prove that impossibility result, but we cannot allow nested calls for functional encryption because that breaks our proof somewhere else. So this trick is where we use for that second theorem. But okay, so for witness encryption, it looks like the picture is not that scary anymore. We have a bunch of inner calls to the oracle, but they could become explicit and visible if we modify witness encryption without loss of generality, which means that it's safe to pass them. Now there is no hidden queries. We can basically now say that the witness encryption doesn't imply I/O in the extended black box model way, because after I do this, witness encryption behaves more or less like a random oracle. And the random oracle, we already know how to compile out from its previous work. The oracles that are not doing something fancy are just basically an injective random function. You can compile them out. So that part is relying on previous. So after you, so let me say it this way. Basically, what we are saying is that after you do this trick, you're down with an oracle that has an encryption. So let me say it this way. Everybody who wants to decrypt something, they can run they can run the algorithm F on the witness on their own before really asking any decryption query. So let me say it this way. So we can canonicalize every piece of code that uses witness encryption. If you are about to call a decryption query, I'll say, wait, first extract the circuit F from it. What does it mean? It means that the reveal is used. Reveal is basically just saying that I have a image. I just reveal half of it to you. It's available here. Then you can run the F on your own.
So I guess my question is the following, that in functional encryption, you could also just have two random oracles, right? One that gives you encryption, one
Yes,
that gives
yes,
you
yes.
keys, and then I can keep my lookup table.
Exactly, exactly. What is the huge difference is that here, eventually, what the oracle is providing you with is the following. It has a random oracle, and then it either reveals to you the first half or the second half. The first half is F. The second half is M. That's all it does. In functional encryption, so it's all or nothing. You either learn F or nothing about it, or either you learn M or nothing about it. Functional encryption, you learn F of M, which is one bit of information. So this is previous work.
FW is not, functional encryption, FW is not key. There is no reveal C given yet.
No, but given the secret key.
Amit is asking.
So,
Secret key can be F comma secret key, right? Secret key for F can be F comma secret key.
so if what he is describing right now is for the case of instance revealing witness encryption. He's next going to explain for the case of predicate encryption.
Amit is asking to compare to functional encryption. That's a different direction. So for function,
Issue would be better with the predicate encryption.
no, they're orthogonal. So for predicate encryption, the issue is that, so
And where would this particular proof fail?
let me tell you. So this, after you apply this trick, your oracle becomes kind of simpler. Your oracle, it looks like without loss of generality, I can assume that whoever calls the decryption algorithm, they would only call it when they know that the test is going to pass. Okay. After you apply this transformation, your primitive, your oracle, you can see it differently in a much simpler way. Your oracle is now the following oracle. You have an encryption, which is a random oracle. You either reveal the first half of it for free. Sometimes, after someone does the test on their own, you reveal the second half. So it's like you either see the first part or the second part. You don't see anything fancy about the relation between the first two parts. My point is that this oracle is a simple oracle, behaves more or less like a random oracle, even though it's not a random oracle. Sometimes you reveal half of the input bits. The previous work,
In this case, it just looks very random oracle-like, which is what allows you to compile it out.
yes,
Whereas for functional encryption, it won't.
it becomes a fuzzy thing. So the function encryption, every time you might gain a little bit more. So the previous work already showed that if an oracle is such a simple oracle that is almost random oracle or very close to it, you can, when you run that learning heavy query enough number of times, you basically learn enough information that the next query is either one of those or it's kind of independent. So this 0-1 property is used in previous work that, for example, just work with one-way function or random oracle. And what we are addressing here is that suppose I want to reduce my problem to something very close to what is solved. The only catch for witness encryption is that there are some hidden queries there. I just made them visible, and now kind of we are back to what we had before. The direction that functional encryption goes, it's an orthogonal challenge that we do not know how to handle. So
We can handle
we can add this trick, but the other challenge,
Right. No, I'm saying, and of course, there is no solution since we know that functional encryption doesn't affect IO.
yes.
Okay.
So,
Can you back, actually,
yes.
here, actually, next slide. Next slide.
Next, okay.
Right. So presumably for E prime, you're going to be able to evaluate it on other x's that you didn't encounter in the learning phase.
Yes,
So you need to argue that the B prime is an approximate.
yes. You just have a weak guarantee that when you run B prime on a random point, just like, you pick random points, x1 till xt in the learning phase. If you run B prime on a random point, with 99%, you are going to get a correct answer.
But on these other new points that you're querying B prime on, those might be inconsistent with the ones that you're already.
So think about random oracle. Random oracle, if 2 points are different, their answers are different, independent. So if I have discovered what was likely to be asked by the algorithm B that hits what happened in O, I have already discovered that, covered that in those executions. These are all older ideas, so these are not our contributions. Our contribution so far is just to say how I can turn the seemingly challenging task of working with witness encryption with 2 layers to something without 2 layers. And the oracle becomes close to random oracle. We know how to compile it out. By the way, something important is that we now are allowed to compile out the procedures in 10 steps. We don't have to compile them in 1 step, because then you can compose everything. So because this idea allows you to start with an approximately correct I/O. So every time you little bit of correctness, you don't have to start from a perfectly complete I/O. Therefore, compiling out in 10 steps is okay, and that really simplifies the job, because we can, if we have a primitive with 10 subroutines, we can compile out the subroutines one by one. So it really simplifies the job. But anyway, so witness encryption so far seems kind of easy. What we show is that witness encryption with some cheating implies attribute-based encryption, and attribute-based encryption couldn't give you I/O. Everything now for free comes in the extended black box model, because the transitivity theorem there. Now, I should actually, so this is not a corollary anymore. Oops. This is really. So now I just want to briefly tell you what really changes when you go to the next primitive. Now I don't want to talk, the witness encryption was a natural primitive, but the other versions are not. What we care for in this slide is predicate encryption. Predicate encryption is different from attribute-based encryption or witness encryption. It is actually important that the secret that is in the plaintext is not going to be revealed. However, if you successfully decrypt something, then that becomes revealed. And if you can decrypt something, now you can go back and discover what happened inside that. So what we're going to do here is that we're going to define some form of witness encryption that more or less gives you predicate encryption. And that challenge is already built into that witness encryption, which we call it instance hiding witness encryption. It's a witness encryption that you are not allowed to leak the function f. It's actually guaranteed. If you leak it, it's going to be insecure, because the security definition is different. This is the definition. If you have two unsatisfiable functions, and if you encrypt M0, M1 under these two, that should be indistinguishable. If you leak the function f, it's not secure anymore. So this primitive somehow demands you to hide f. Therefore, revealing f is not allowed. What does it mean? It means that if I want to do the same tricks, this dark side, the hidden side of the learning algorithm that is not hidden to the learning phase, but we are not allowed to pass it along. What happens is that the idea is that, well, we cannot open it. However, because of the trick that I told you, some of them we might be open. So if you can successfully decrypt something, then it looks like more or less like a witness encryption, that if you can successfully decrypt, after that you can go back and discover everything, which means that if this is a successful decryption, then it's okay to pass the hidden side of it.
So now the new functionality is that upon successful decryption, you do learn what happened.
So I'm saying,
In the definition of instance hiding witness encryption, if you do manage to come to the witness,
yes, then you can.
then it also
Yes, yes,
yes.
yes. Then so we kind of add a weaker leakage there.
Sure.
The leakage is conditional. Only after you successfully decrypt, you leak.
That doesn't have to be, you could imagine witness encryption that doesn't have that property.
You can imagine what?
Witness encryption that does not have that property, even if you.
Certainly, this is a strengthening. This is a strengthening of witness encryption, which says you're supposed to hide it according to this definition. I'm saying now, suppose this is your primitive. I can safely add another reveal subroutine that after you decrypt successfully, you're going to.
Imagine an instance hiding witness encryption, that even after successful decryption, the instance is still hidden. Does not just give you I/O. That would be
Okay, that's a strengthening, yes.
Any strengthening of it will go beyond.
Sure. But this middle primitive is enough for predicate encryption. Maybe the primitive that you're talking about, maybe that gives me even better. So if I can handle that primitive, maybe I can get more separations. But this was enough for predicate encryption.
And in particular,
Yeah, this is basically visible.
That's also 0, 1 primitive.
This is basically zero. Yeah, I didn't want to introduce. So basically, what happens is that some of these hidden clouds become visible, and some of them don't. But what we show is that the analysis becomes much more complicated. Basically, if you just look at the ones that you have managed to open up, and the point is that the process could continue. When you open up one of these circles, you might be able to open up another one, because you might be able to find a pre-image of a ciphertext, then another one gets open, another one. These things propagate.
And I guess the intuition is that if you didn't open it, then it was kind of useless to begin with.
Yeah.
That's true. That's true.
Because the 0, 1. Right.
That's true.
All or nothing.
Yeah. Very
At the end of the day, we can manage to only open some of them, but we go as far as we can. If we open this one, we look inside it, we learn a little bit, we go somewhere else, we open it up, we get stuck somewhere. We say that if you get stuck, and modulo some other tricks that we have added, we have to actually now run the learning algorithm random number of times for technical reason, because if you just fix the t, maybe that particular t is a bad thing, but if you pick it at random, things become good. But nonetheless, the analysis shows you that half leakage is enough for your approximate execution. That's basically what's. Now, I listed other primitives for you. I told you we work with other variations of witness encryption. The other primitive, homomorphic encryption. Homomorphic encryption, fully homomorphic encryption, has similar challenges like predicate encryption. When you run an evaluation algorithm, you don't see what happened. You cannot really open it up. You again have to do the hardware of trying to say, if I have managed to decrypt my ciphertext, then I can look up what happened inside. If you are running evaluation over something that you know every single ciphertext, you can open it up. But in this approach, how we deal with it, we actually define some form of homomorphic witness encryption. We say, if you have a bunch of ciphertexts under the same F, you're allowed to do homomorphic operation on them. So if you define this, which is simple, that's it. That's the definition of homomorphic witness encryption. We show how to use it basically to get fully homomorphic encryption, and we show why that homomorphic feature that we added to the witness encryption is still okay. We can still compile it out, even though it's calling itself nested way. So we don't really work with the function fully homomorphic encryption, which has like 4 subroutines. The witness encryption is a simpler one that we can kind of work with. If the kind of this, again, part of the separation is we are pushing it to the positive results, which doesn't carry the main ideas of the impossibility. Okay. Let me finish. I guess I'm over time. But what I'm... the summary is that basically what we show is that if you want to get I/O from a bunch of great primitives, that in order to kind of have one feature in mind that lets you remind them quickly, is that they all are basically everything that is an all-or-nothing encryption. Functional encryption is not like that, because I/O is not like that, because you learned a little bit about circuit itself. So I/O and functional encryption are kind of fuzzy things. Things that are not fuzzy are 0, 1. Even though they're so powerful, they're able to run codes that potentially have secrets. Even by using that feature in the most general way that you can imagine, none of them is going to give you I/O. And something that I didn't talk about, but maybe I can say now, you're even allowed to throw one-way function gates in those secrets. You're allowed to throw in constant degree graded, everything that we have previously proved the separations for, because what we are doing, we're reducing the previous work. We are saying I compile out my Oracle gate subroutine by subroutine till I'm left with something that I have previously shown how to compile it out. So if your circuits are having trapdoor permutation gates or even constant degree graded encoding gates, you still cannot use it to get I/O. And probably the most kind of obvious thing coming out of this work is that now that we start to prove impossibility results that are kind of meaningful for non-black box techniques, basically we are plugging in, we are making this popular non-black box techniques built into the model. Well, can we now go and look at other impossibility results that we should prove now in this model? Because we have also rather in-depth study of the model that we use a lot of lemmas that we develop in our separation results. So you might want to look at that on its own. Thank you so much and if you have more questions, let me.